So welcome everybody. When we were talking last time, we were making the group orbitals for a trigonal planar methyl, CH3. In this case, we were envisioning CH3 cation. And we were going to take those orbitals, which are shown here over on the left, and we were going to distort them into pyramidal methyl. And what we're drawing here is going to end up being what's called a Walsh diagram after the chemists that sort of developed this qualitative approach. And as we do this, we're going to use one of the rules of qualitative molecular orbital theory, or QMOT, which says we're going to make systematic distortions from high symmetry structures like this trigonal planar group, and then decide how that's going to change the energies of these orbitals based on how orbital overlap changes. So last time we said if you take this mostly S character CH3 group orbital and start to pull the hydrogens back towards the left to make the carbon more pyramidal, the energy doesn't change a lot. The overlap between carbon and the 1s orbitals doesn't change much, but you start to get maybe a little bit of hydrogen-hydrogen overlap. Now, remember, this orbital is where two electrons are going to go. It doesn't correspond to any one bond. Remember, in MO theory, we're forgetting about bonds mostly, and we're just considering electrons delocalized across the whole molecule. So even though it's nonsensical to say, from a valence bond point of view, to say that this hydrogen is partially bonded to this one, there is some of that character in this particular molecular orbital. Not enough to make it go down in energy very much. Okay, let's think about how the distortion to pyramidal is going to change these orbitals B and C. Okay, so again, I'll start with the distorted B. There's my p orbital on carbon, and then I'm going to have 1s orbitals on each of these hydrogens, and it looks to me like the overlap is not quite as good, because whereas before the p orbital on B was sort of oriented to right in between those two 1s orbitals, over here they're not directly end-on. So the overlap is a little poorer, not a whole lot poorer, but we would expect perhaps this B orbital to be just a little bit destabilized. Not much, but a little bit destabilized relative to the corresponding orbital in the planar methyl. And of course, the same thing's going to happen to the other planar methyl orbital. Here's the hydrogen that's in the node. We still have a p orbital that's in front, one lobe that's in front, and the other's in the back. Coloring. We're going to still have orbital density on the hydrogen that's out in the front and the one that's out in the back. But overlap isn't going to be quite as good. Okay? Now, it turns out that, well, we'll consider that a little bit later. All right, so with me so far? Go ahead.
So with these p orbitals, is our like XYZ coordinate frame of reference arbitrary? Like we just kind of pick one and stick to it?
Yeah.
Or
That's right. Our XYZ coordinate frame of reference is arbitrary. I forget what we decided. I think it was X up here and Y here. What matters is on the carbon you have an alphabet of 3 and they're orthogonal to each other.
But I'm thinking, like, could we like rotate our frame of reference so none of the hydrogens are in a node?
Could you rotate your frame of reference so none of the hydrogens are in the node? You could, but at the expense of overlap. I'm struggling to think of exactly what geometric translation you'd have to do. And you probably could do it, but
This is the most stable.
the overlap would be poorer. Yeah. Other questions? I think we alluded to this last time, that something interesting happens with this D group orbital, which is just basically the unhybridized 2p or 2pz orbital on carbon. Because before, all 3 hydrogens there were in the node of that orbital, and so there could be no orbital density on those atoms. But now we're going to pull them back, and now they're out of the node. Let's see. Struggling to draw. Now they're going to be out of the node, so now all 3 can participate in that orbital. So if we were to just draw it this way and then continue to draw the 2pz orbital on that carbon, we'd end up with something like this: pink phase in the back, yellow phase in the front. And we'll see that this is going to go down substantially in energy, because whereas before there was no bonding interaction at all with these hydrogens, now there is. Okay? So that's going to be a substantial decrease in energy. And, you know, the precise amount isn't that important to our discussion. But that's what we're going to get when when we distort the molecule out of planarity. Yes, Kim.
So we just arbitrarily decide that they're in phase with that lobe. Like, if we chose to make them out of phase with that lobe, is that just...
That would be the anti-bonding combination, which we haven't drawn, but it does exist.
Okay, gotcha.
Yep. Yeah, there's a reason your text goes through this, and there's a reason your text jumps up to this highest energy orbital. You don't have to, but you could draw all the other ones that are sort of in between D and G. There would be one that's the out of phase combination where it would be yellow here and pink there. And then there would be another 2 that are out of phase versions of these 2 pi orbitals. I forgot to tell you that these 2 orbitals that are degenerate with each other, we're going to call them pi CH3 type orbitals. And the reason for that is that if you sort of take a step back and view what they might look like from an actual calculation, you can see that they resemble more than just a little bit a p orbital. Like if you squint a little and forget that there's actually a CH3 group under there, you'd have thought, oh, that's a 2p orbital. It can participate in pi type bonding. Okay, and then of course the one over here would look basically the same, only sort of tilted on its side. And so we're going to name these according to the kinds of bonds they can participate in. This is a sigma CH3 orbital because sigma bonding is end-on-end overlap. Pi bonding is side-to-side overlap. We're going to call this one that we've just drawn, let's see, I need to change color. We'll call this one sigma out because unlike the sigma CH3, it has a lobe that projects out into the space between the two carbon atoms. All right? So we'll call that sigma out. Okay. What else? And then if we were to distort the antibonding sigma CH3, from planarity, we would end up just with what you would expect. There's not going to be a huge energy change as you go here from pyramidal to not. Because there is a spherical node in between the orbital on carbon and the spot of the orbital that's on hydrogen. So there would really be not a huge change in energy there because there wasn't any overlap to begin with. All right. Other questions? All right, so now we're going to do something that's unusual and is going to seem arbitrary, and that is we're going to notice that we'll maybe call this sigma star CH3 because it's the antibonding combination. We're going to notice that the two highest orbitals with sigma type symmetry are different in the kind of orbital that's on carbon, right? Do you see how in sigma out, the atomic orbital that contributes to this MO is the 2pz on carbon, whereas up here it's the 2s, all right? That puts us into a situation where we can apply rule number 7, and I don't know that you can derive rule number 7 from first principles. It's probably more of a mnemonic device to get you to what the right answer is in terms of MO theory. But it says when you have this situation where your two highest orbitals of sigma symmetry differ in the identity of the contributing atomic orbital at carbon, what you do is you mix them together to generate two new hybrid orbitals that look like this. And actually, it makes sense a little bit when you think about the relative energies of s versus p orbitals, right? If we're going to fill this sigma out orbital, it has p character here, right? Whereas the sigma star has s character on the carbon. Of course, we'd like it to be the other way around, where the lower energy orbital has more s character, so that the electrons can be held closer to the nucleus and be more stable. So, in response to that, we mix the two, and that allows us to go down in energy even more, because we now are going to have increased s character at carbon. And if we were to draw this orbital, now it's going to look like our conventional sort of sp3 hybridized orbitals that we learned to draw from valence bond theory. Oops, wrong color. And the one on top is actually going to get a little higher in energy because we've taken away some of the s character and replaced it with p character. And we've also introduced a more directional antibonding interaction once you see what this sort of looks like. All right. Yeah, Kim.
The loaf that gets fatter, like, it seems kind of random how they choose.
Yeah.
It would make more sense to make the pink loaf fatter and the sigma smaller end of one, so like how are they deciding which lobe gets fatter?
Well, it turns out that this is in what I've drawn it's a good question if you think the orbital looks exactly like I've drawn. In reality, this sigma out orbital looks like it has an enormous lobe here that has a node at carbon and then covers all of the space between carbon and the hydrogens. And then a little bit of a smaller lobe there. In terms of why I drew it the way I did with the larger lobe pointing out, I did that because I don't know what the answer is from first principles. I did that because this orbital has significant carbon-carbon bonding character, and in order for that to happen, you're going to need it to be pointing towards the space. Like if you were going to bring two of these together, there'd be one methyl group here and another methyl group here, and they'd come together to form a bond, and you want overlap there.
Yeah, that was something else I was a little confused about. They kept on talking about like, you can tell this orbital has carbon-carbon bonding character or carbon-hydrogen bonding character, and is it just referring to the fact that like there aren't nodes?
Yes. Yeah, when you're talking about what kind of bonding character an orbital has, you're just looking for in-phase overlap between atoms in a particular orbital. So there's no carbon-carbon bond here in CH3, but you would say this has carbon-hydrogen bonding character. Yeah. Okay, other questions? Yeah, Mario.
So does mean that they mix orbital G and D, so to give different energies to the both orbitals at one, that is D give more S character, and in G you have less S character.
That's exactly right. That's exactly right.
Change energy. So this will tell me that the difference of energy are more bigger. So this is the idea of the rule.
Right. The question is the idea that D gets more S character and moves down in energy, whereas G gets more P character and moves up in energy. Yes, when you mix them together, they split apart even further. Yeah, good. Other questions?
So just to clarify one more time, you're basically saying that they do this because they end up looking like the molecular orbitals that they calculate, and that makes us happy.
That's right. They end up looking like the molecular orbitals we would expect to see. I don't have the ability to show you what the orbitals look like for, say, methyl cation on my iPad at least, because my Spartan iPad program doesn't do cations for some reason. You got to subscribe to the whatever for like $3,000. So maybe someday. But when we combine two methyls together to make ethylene, I will show you how what we're predicting is exactly what the calculations say. And we haven't done any math. All right. So, other questions? This allows us now to do some things that previously we needed valence bond theory and VSEPR to do. So let's ask the question, why is CH3 plus planar, whereas CH3 minus is pyramidal? Okay? And to do this, what we're going to do is first imagine CH3, and CH3 plus has how many electrons? 6. Okay. So actually, for the sake of our discussion, I'm going to just copy this Please don't redraw it in your notes. That would be silly. CH3 plus, we've got 6 electrons. So let's populate the orbitals from lowest to highest and see what configuration gives us the better energy. And remember that on distortion from planar to pyramidal, our lowest energy orbital A gets a little bit lower in energy due to increased hydrogen-hydrogen overlap, whereas the pi orbitals are destabilized due to poorer overlap between carbon and hydrogen. All right. So, which do you predict is better? Which hand is my left? Okay. You know, almost 50% of the time I get that wrong. So at that stage, it doesn't even matter that you know which hand is right versus left. You just pick one, and then if it's wrong, I think it's genetic, actually. They used to tell my grandpa, my grandma tells a story of telling my grandpa, Dale, throw a rock, Dale, throw a rock. He's like, oh, right, that's my right hand. Right, so if you look at the planar one, yes, the lowest energy electrons are not as low as they could be, but that modest decrease in energy for orbital A upon becoming pyramidal is not enough to compensate for the fact that you have 4 electrons that are now at a higher energy level. So, and even if, I think this amount of destabilization here, if you calculate it, is worse than the amount of stabilization you get. Even if it weren't, though, you got 4 electrons versus 2, and that could tip the balance, okay? So we just predicted with some drawing, some rules, and some simple energy arguments that CH3 plus is planar. We didn't even need VSEPR to do that. We didn't even need to talk about electron-electron repulsion. It just fell out of the picture of the MOs, all right? Now, what if we modified this and said, okay, instead of yes. Yeah, the question is, can I explain again why we know that it is planar? Yeah. And I'm zooming out so we can see the whole figure. We have 6 electrons, and so we're only going to populate the lowest 3 energy orbitals. When we go from planar to pyramidal, the pi CH3 orbitals get higher in energy. Though when we go from planar to pyramidal, the lowest energy A orbital gets a little bit lower in energy. The stabilization that the A orbital experiences is not enough to compensate for the destabilization of the pi CH3s. So if you were to take CH3 plus and make it not be planar, the pi electrons would move higher in energy. And so the lowest energy state for methyl is going to be planar. For CH3 plus is going to be planar. Now, I'm thinking of how these notes are going to look when I copy them and upload them to the Learning Suite. So I'm going to repaste this and we'll do methyl anion. Oh, yowza. Okay, so methyl anion, CH3 minus. Now we've got 8 electrons. Now, you already know that methyl anion is pyramidal. Why? Go ahead.
Because with VSEPR it has a lone electron pair, and that coupled with 3 hydrogen bonds makes it pyramidal.
Right, so VSEPR, you were told electron pair repulsion means electron pairs need to be as far apart as possible. You were told you can think of lone pairs as being bigger than other groups because they're electrons that are not involved in a bond should be more repulsive than those that are involved in bonding, and that works to give you the right answer. But in terms of our MO picture, it's this difference between the p orbital in planar versus the sigma out orbital. And I'm sorry, I should have just put these electrons over here. The sigma out orbital in d prime. Yeah.
So the sigma out orbital is what we consider the final result of the Walsh diagram. That little thing in the middle is just like an intermediate
Conceptual
step.
intermediate.
Okay.
Yeah. Yeah. And right, when we go pyramidal, the significant amount of stabilization we get by introducing new carbon-hydrogen overlap and by rehybridizing to an orbital with more s character more than compensates for the modest destabilization of the pi orbitals. Okay, CH3 minus, what's the HOMO of CH3 minus? It's our sigma out orbital. How does that compare with what you might have thought about previously? What would you have said before about what you think the HOMO of CH3 minus is? Yeah, I taught my students in 351 that, it's the non-bonding lone pair. Is that still true? Sort of, right? You have a lot of orbital density right where we would have picked a lone pair to be. And in fact, if we had ever drawn a lone pair orbital, we might have just put a lobe there, and that's where it is. The nuance is that those electrons also have some CH bonding character. Okay? So you can think of this as being sort of like the lone pair on CH3 minus, but you've got some carbon-hydrogen bonding character mixed in. We could do the exact same thing to compare BH3 and NH3. One of the great assumptions of this QMOT thing is that if you construct group orbitals for a particular symmetry, it doesn't matter what the central atom is, right? It could be carbon, it could be nitrogen, it could be boron. I don't know, probably want to keep things within the same row of the periodic table, but so you can use exactly analogous arguments to show why ammonia is pyramidal, whereas BH3 is planar. Okay? Yeah?
So if we did an MO diagram for CH4, it would just keep going down, and that's why like CH4 is more stable than CH3.
Right. If we were to do an MO diagram, we could try to make methane by mixing these 4 orbitals with a 1s on hydrogen. And if you think about where that other proton would be, it would be here in phase. If you put the other proton here, it would need to overlap with the yellow part of the p orbital. If you put it here, it would be in the node. And if you put it here, anyway, it gets, I'm not sure it works to do that with methane. I'm not sure why. It's a good question. But in general, yes, when you do methane, it turns out the way you arrange things brings this d orbital down into degeneracy with the pi orbitals. And so you have 3 orbitals that are equal in energy. I will show you for fun the program Spartan as implemented on the iPad. It's a $10, I think, app, but if you decide you want to have one to play around with it, it's kind of fun. So I'm going to put nitrogen there, and we'll go ahead and see what ammonia looks like. We'll download things, and then we're going to look at the orbitals. Ooh, what does that look like, folks? You have a lowest energy orbital, 2 degenerate orbitals, and a higher energy orbital, exactly as we predicted. So let's have a look. Unfortunately, that's not transparent, and I'm not sure how we can view it from the side. There we go. Try to put it sort of in the same configuration as it was in our drawing. Okay, that's our sigma orbital. Let's see, then we can tap the higher energy one. Let's see, so here is one of the pi orbitals, and then this is the one where the hydrogen's on the node. And then what is the HOMO? Oh, let's have a look at that. That looks like mostly non-bonding lone pair on the nitrogen with some NH bonding in the back. All right. I guess another thing well, no, that's fine. Anything else you want to see? Do you want to see BH3? That'll be our surrogate for methyl cation, so you can see what the orbitals look like planar. There's our lowest energy orbital, and there's one of the pi orbitals, and there's the other, and again you've got a boron hydrogen bond that's in the node. And the LUMO is the empty p orbital. Yeah?
BH3 then chooses to be planar because it has the same number of electrons as methyl cation?
Yes, same reason BH3 would be planar is because those pi electrons are going to get destabilized when you go pyramidal.
Yeah, and same thing because if NH3 has the same number of electrons as
Yep,
CH3,
as CH3 anion.
So the orbitals are similar.
Yep. And that's an interesting feature of organic chemistry that we could mention. If you look at NH3 and CH3 minus, we could call these isoelectronic, because even though the atom changes, the number of electrons are the same and the orbitals are very similar. The difference is the electronegativity of the nitrogen. And in general, what you'll see, one of our QMOT rules is that when one orbital is more electronegative, it's lower in energy than the other one. So the effect of going from carbon to nitrogen would be for all of the orbitals to go lower in energy, which incidentally is the reason why CH3 minus is such a better base than ammonia, right? Just look at the pKa's of the conjugate acids. All right, others? So we can do an analogous approach with bent and linear CH2 groups. I'm trying to think. But actually, and I can refer you to the book and to my notes on that. The process is very similar, and I don't know that there's a lot to gain by us walking through it in class. One of the interesting features, though, that I want to mention without sort of deriving all of it is, let me just copy it. On the left are the orbitals you would construct for a linear arrangement of carbon and two hydrogens. You've got a bonding sigma type orbital, you've got a bonding pi type orbital, and then you've got two unhybridized p orbitals. And if you were to fill them up, for example, in water, this is what you would get. In contrast, if you generate a bent CH2, You have small stabilization here for the same reason due to hydrogen-hydrogen overlap. Small destabilization in the pi CH2 because of poorer overlap between the lobe on the P and the 1s. You get large stabilization in the sigma out orbital, which used to be the 2pz orbital, because again, you're introducing a CH bonding character, and then really no change in the stability of the other p orbital. Interestingly, this tells you for water on its own in the gas phase, the two lone pairs, which would be these guys, highest energy orbitals, are not equal in energy. How many times have you drawn or thought about lone pairs on water as being spotted rabbit ears, right? Yeah, and actually that's not a bad approximation for what happens in solution. When water molecules are near each other, you break the symmetry, and that actually can cause some rehybridization of these two orbitals to generate two, so roughly sp3 hybridized orbitals for the lone pairs. But on its own, in the gas phase, what you've got for water is a lone pair that is rich in S character and points sort of directly out away from the oxygen, and then a lone pair that is orthogonal to that one that has P character. Yeah?
So that sigma out orbital, why is it sigma and not pi? It looks like it's got the node then.
It does have a node, but this, we call it a sigma out orbital because this, if it were to engage in bonding, it would be sigma bonding because it's got the large lobe on this side. Now you were right, you could line it up in such a way as to do pi bonding, but it won't do that. And because of your two p, x, y, and z, you can have two orbitals. You can have up to two, I guess, that could do pi bonding, but the rest, I think, have to be sigma. Because otherwise, you're going to give up end-on-end overlap. All right. So now let's make a bond. How to do this? Well, or let's actually make a molecule. We can start making larger molecules by simply combining and mixing together group orbitals. So let's think about the MOs for ethane, okay? And we probably are not going to get through all of this, but once we do, you're going to see how our predictions are in general going to be right in line with what the MO calculations tell us. All right, so we'll start low in energy with our group orbital for ethane. The lowest energy one was the, let's see, sorry, the lowest, wasting time with color. There's always time for color. You guys, I don't know, are you too old or young to have seen the, by now, Christmas classic Arthur Christmas? Anybody seen that? No? Okay. Probably worth looking up this Christmas. It's pretty funny. Anyway, there's a little elf there who says, there's always time for a bow, and there's always time for color. All right. So we're going to mix the two. And if there were an efficient copy, paste, and invert function in Notability, I would save us some time, but as there is not, we'll just color along. All right, mix these two orbitals together. We're going to do that in phase and out of phase. These orbitals are pretty low in energy because they have all S character. Okay, sorry. And I need to get rid of that horrific floating. You'd think that would be default. Hide floating eating controls if I wanted to. Okay, so you're going to mix these two together in sigma fashion, but notice those two s orbitals are not directional, so there's not a lot of good end-on-end overlap. It's just sort of it's not as good as you would get if there were, say, some p orbitals there. So we're going to go down in energy a little bit, and remember that the amount we go down in energy is always lower than the amount we go up in energy. So let's go down 2 squares and then up 3. So our lowest energy orbital is going to look like this, and we get it from combining the 2 sigma CH3s of our methyl group. And then the next one should just be this, but have the out of phase combination. I need to decrease the size of my eraser. Dang it. Bloop, 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 bloop. Now, you might ask, hold on, this is an out of phase combination. Doesn't that mean it's an anti-bonding orbital? Well, our concept of bonding versus anti-bonding orbitals makes more sense in the context of valence bond theory. We don't worry about bonds anymore for MO theory. So it has bonding. It does have carbon-carbon anti-bonding character because there's a node between the 2 carbons, but you still got carbon-hydrogen bonding character, right? So that's still a bonding orbital. Go ahead.
We don't consider it non-bonding then, because anti-bonding and bonding character are both present?
No, because it's a good question. Would you consider it non-bonding because you've got both characters present? No, because there's more bonding interactions than there are anti-bonding interactions, which is just shorthand for saying the math says this is the second lowest orbital in energy. Okay. So if you recall next, let's see how far we're going to get. We still got a little bit of time. Next, we had our B and C orbitals, and our B and C orbitals were the pi-type orbitals. Drawing circles. I don't know why Notability doesn't come with preloaded copy and paste features for MOs. Wouldn't that be nice? All right. So filling in the back. Okay, you've got your pi-type orbitals there. Of course, on the other side, we're going to have the same thing. No? Oh. Needed to zoom out a little bit more.
Josh, not to interrupt, but
That's okay.
we're using the non-planar ones because we're trying to form a bond between 2 carbons.
Right. Why? Okay, that's a really interesting question. Why should we do it this way when we could instead use the 2 planar CH3s? It's a good question. And you can do that. If you try to make a bond between the 2 planar ones, what you would discover is, and you would probably have to actually do the math to compare it, but it really will come down to that sigma out pair of electrons, which is going to be so much lower in energy when we pyramidalize because it's going to have S character and have carbon-hydrogen bonding character. Good question. All right, so we got to draw our other pairs over on this side, which I'm going to do mostly because I'm obsessive and cantankerous about it. You don't have to redraw the same orbitals over here if you don't want to. It'll save me some time because I'm going to just bring them together to form our new bonding orbitals. What in the heck am I doing? We don't know. Yellow in the back. All right, so we're going to make two in-phase overlap type orbitals by bringing one of the pi CH3s together with the other one. Decently close in size. And then we'll bring the other two together that have the same kind of symmetry. All right. And these are both pi CH3, so these are the pi plus pi combinations. And then we would also draw the out of phase combinations. But before we do that, let's just review where we are, take a step back, and I want to demonstrate that even at this stage, we have predicted what the lowest 4 energy orbitals in ethane should look like. But I'm going to pause for you to catch up a little bit, pause for what questions you might have. Yeah.
This might just be how they're drawn, but it kind of looks like if we were to fudge this into a molecular orbital, that the one on the right would have 3, or do they just have 2 nodes? They just have 2 nodes each, don't they?
That's right. If you wanted to draw what? Which one on the right?
Never mind. I think I'm thinking of an antibonding orbital.
Okay. If you wanted to draw a node here for this pi, it would be sort of the plane looking on the side, whereas for this one, it would be sort of the XZ plane, up and down, plane of the page.
Pink hydrogen in the back.
Oh, no, yeah, coming out at you, and it's just my poor drawing skills. I'm sorry, I'm worrying about those stray marks. Doesn't have to be pretty, Josh. Okay, so other questions? So let me just show you in Spartan what that looks like for ethylene. And now you're sort of understanding why we don't do this in sophomore organic, because we're like 3 weeks into the semester and we just got to ethylene bonding. All right. And it's not ethylene, it's ethane. Dang it. Oh, I wrote ethane. I'm saying the wrong thing, though. Okay, so lowest energy orbital. Okay, that looks just like what we drew. We'll zoom over there and see what we drew to confirm that it's actually looks like that. Okay. Next highest orbital, the out of phase combination, but still CH bonding. Then the next, you've got these two degenerate pi type orbitals. Here's one that has a, I think in our case, the way we drew it, the node was in the XZ plane, and then the other one has a node in the XY plane, or I'm sorry, YZ plane. Go ahead.
Oh, I think Colin is trying to raise his hand.
Oh, sorry, Colin. Go ahead. Can we hear you?
Maybe, I'm not.
Audio controlled. Try again.
I was trying to tell you that the video is stopped, so we're not seeing what you're showing right
The
now.
video is stopped, so you're not seeing what I'm showing. I am so sorry. Let's see whether we can.
Oh, I think it's because screen sharing was paused.
Screen sharing was paused. Dang it. Is the Zoom meeting even running?
Well, they're there.
New share. I'm very sorry, Colin. Thank you for making that known. The recording will be available, so you will be.
It still says sharing is
I
paused.
think you have to click resume share. Click that little link.
Oh, thank you. Stop share. Start share. Share, huh? Do you believe in it's. Can you see anything now? Still no?
No.
Okay. I think
Just the black screen.
just the black screen. Okay. Well, we're out of time anyway, you guys. So I have recorded what we have been doing so that you should be able to check it later. I'm sorry that Zoom was weird. And we will start where we were next time. I am so sorry, Colin and Samantha, but check the last few minutes of the video I'll post right after this class, and you'll be able to see what we were talking about.
Okay, sir, thank you.
Sorry.